Good morning, everybody. Happy Monday. If you could start with some green check marks, and then we will get started. Hopefully you guys had a great weekend. I know that the schedule on the homepage wasn't up right away, so happy to see a few people here at least. I don't know if Mrs. Woods put that up yet or not. The image, for whatever reason, wasn't loading properly, so sorry. You're here now, though, which is good. So we're going to do a little bit more on what we discussed last day. And we have class today and then again on Wednesday, but we have kind of longer blocks. Great, thank you, Taylor. We have longer blocks, so we're going to get some stuff done. We're going to actually finish off the Unit 10, the Earth Science stuff. And then we have 2 weeks off. And I have mentioned a few times that I'd like it if you guys finished Units 1, 2, and 3 before the break, because they will not be open after the break. We're just going to, if you're not done the first 3 units before the break, then you're just not going to make it through the end of the course, essentially. And it's not likely that I'll get to very much over the break. I'm going to be having a break, and I encourage you guys to get as much done as you can before then and take 2 weeks off. What a great opportunity to spend some time with your family, friends, go outside. It's been pretty nice. Eva, I was looking at the questions for 10-2, wondering if we do question 1, if we're doing the plate tectonics assignment. I'll look at that here in a second, Ava, maybe in a few minutes. And Anna's asking when Unit 10 is due. We're going to finish Unit 10 before the break. So if you're completely on track with everything we've been doing, you should be done Units 1, 2, and 3. You should be done at all of those tests as well. And you should probably be done the Module 1 exam, which is kind of the first 3 units altogether. A few people had gone through it over the weekend. I had a look at the marks this morning. They're good as always, but I looked at how long it took everyone to do it, and it was about 10 to 20 minutes for the few people who had done it. So it's not like a extremely long test. It's just more questions, 36 questions. So not meant to be difficult, just more of the same. And it didn't take very long for those people who did it. Maybe we'll jump into the Unit 10 learning guide here and see if I can help you guys out with that. I loaded the plate tectonics activity into the course. So I'll just scroll down. Plate tectonics inquiry. And when we left last day, I asked you guys to go in and have a look at it and just play around with it. And I'm hoping today, once we finish class, you'll be able to go in and actually do the assignment. So we're going to be talking about this plate tectonics stuff today. And I wanted you guys to just maybe be a little bit familiar with it before we started into it, just so you could, see if you understand things a bit better, having seen it before I talked about it. So that's there. But Eva was asking about the 10.2 learning guide questions. Let's just scroll on down to those. 10.1 practice for continental drift. So you should be done that because we've done continental drift. And we're going to get through all this plate tectonic stuff today. We're not going to get to the earthquakes, I don't think. Well, we might actually. Volcanoes. Complete the 10.1, 10.2, check your understanding. Are you talking about the virtual earthquake lab, Ava? Doing the plate tectonics assignment. Plate tectonics assignment, 10.2. I'm gonna talk about this stuff here, the virtual earthquake lab, for sure. We're gonna end up doing that probably. I might leave it with you for today so you guys can get it done for next day, or maybe we'll do it next day in class. Just depends on how far I get. So we are doing 10.2 today, you're right. The virtual earthquake lab we will do. I'll talk about it in class. And I think that's probably what you're talking about. So Yeah, we'll have some time to go through that today. The plate tectonics inquiry, since we're here, there was a little simulation you could run with plate interactions, continental and oceanic continental and transform and convergent, divergent, all the plate boundaries that we were going to deal with. And then there was a Word document to go along with it. So I initially just asked you guys to go in and look at the simulation just to kind of play around with it and see what it was all about. And now I'm going to get you guys to actually do this assignment. So it's just 2 pages, not too long. And basically you just go into the simulation, you just go through the questions step by step. It's not a difficult thing. It tells you how to set everything up. It says, select these buttons or do this, do that. Describe the differences between oceanic and continental crust. Predict how changes occur. Predict movement based on composition of the plates. So if you're looking at what the plates look like when they come together or move apart, what's going to happen as a result. So what you do is go to the simulation. You're going to do both tabs at the top. There's 2 kind of tabs you're going to go through. The crust tab is the first set of questions here. So grab the thermometer for letter A. It says describe the temperature. So go in, drag that little thermometer around and see if the temperature goes up or down, just depending on where you are. Describe how high you are, if it's hot or cold. If you go lower, does it get hotter or colder? And what do you think causes the differences? We'll talk a bit about that today. Change the crust into oceanic crust. So you go through that. Have a look at the density. What is the density? Is it, pick the layer you're in. So was it crust? Is it something else? How does this layer's density compare to the picture? Greater than, less than, equal to. Why do you think that is? So that's the first tab, the crust tab. And then you go to the plate motion tab, which is the second one. And basically you're going to look at all of the different types of plate interactions you can have. So it's going to tell you to set it up. Like example 1 says drag an oceanic crust and a continental crust. And then move it in the direction of the green arrow. So you're bringing them together. What happens? And you're supposed to draw a little picture of it. And then what's the outcome? Does anything happen? Volcanoes, earthquakes, what happens? So you just describe it in that regard. So that's kind of the activity. You do the 3 different examples, and then you can just play around and find anything else you found interesting. So I don't think that should take very long. Does anybody have any questions about that? You can download it to your computer. You can do it on the computer, or you can do it by hand. Doesn't matter to me. And then you can submit it with your learning guide at the end of Unit 10. So just like we've been doing, I'd like it to be done for Friday. I would like all of Unit 10 to be done on Friday. So you can do that for Friday. That's the only question. I think we're doing okay. I'm going to jump into 10.2. If you guys do have anything that comes up, let me know. So plate tectonics is 10.2, and we're just going to kind of plug away through here. So this obviously matches up with your notes. Yeah, Taylor, you can print it if you want, or you can do it on the computer. I do not mind either way. I'm easy. So the first thing we're going to look at is layers of the Earth. So the Earth's about 1,200 kilometers thick from the edge to the center. So we're talking about a radius, not a diameter. Obviously double it to get the diameter. And we have these distinct layers that make up the Earth. Now, it's always interesting to think, how far have we ever gone towards the center of the Earth? So, I don't know, in chat, just throw in the furthest distance you think we've gone towards the center of the Earth in terms of, not like a human, but like a drill hole. So remember, it's 1,200 kilometers to the center. Alex is going with 12 kilometers. What do you think? It's 1,200 kilometers from the edge to the middle. So 12 doesn't seem like a lot, but it's a guess, I suppose. Abby's going to just agree with Alex. Maybe you guys are you're on top of it. You already talked about it before, and you know exactly how far we've drilled into the center of the Earth. Haven't you guys ever watched that beautiful cinematic masterpiece with Brendan Fraser that is Journey to the Center of the Earth? Alex, you've already seen the documentary. You ruined it, man. You ruined it. Anyways, we'll talk a little bit about it. So again, I don't love memorization, but unfortunately you have to know the layers of the earth. And this isn't something that comes up in your learning guide, so you can't just refer to an image. You just need to know what they are. So you end up with the crust. That's where we live. We're on the top, we're on the crust. And then you have upper mantle, lower mantle, and inner core, outer core. So you don't need to memorize the thicknesses of each of these, but you should have a general idea of how thick they are. So the crust, in general, is between 5 and 70 kilometers thick. So we're going to talk a little bit about the lower limit and the upper limit and why those are. And then you have this upper mantle. It's about 600 kilometers thick. And then the lower mantle, 2,000, and the outer core, inner core, another 2,000, and then another 1,000. So they're pretty thick. The consistencies of these things are also important. That's what's here in the notes. So the crust is hard. It's kind of granite. This is what we walk on. So if you go and you see just rock exposed next to your house or in a rock bluff somewhere, it's generally like a granite type rock, and it's hard. And then the mantle, it has two parts to it, the upper and the lower. And the mantle is mostly solid. And then the upper mantle, we call it like a thick toothpaste, but that's not even true. It's even thicker than that. It's somewhat fluid, but it's very, very, very dense. So don't think of it like water. Think of it more like even thicker than toothpaste, kind of like almost plasticine almost. So really thick, like a clay almost, but not clay. It's hot, it's molten. It's hard to describe because we don't have anything to really, in our everyday lives, that kind of looks like it. The outer core is liquid, which is pretty cool, and we'll look at some really interesting things that happen as a result of that. So it's so hot in the core of the earth that there's this liquid outer core. So the metal, iron and nickel, at that sort of temperature, they're actually a liquid. So it's so hot down there. And then the inner core is solid iron, and there's an absolutely immense pressure and temperature down there, and we'll talk about why that is in a second. So I asked what the deepest we'd ever gone down was, and Alex knew it was 12 kilometers, which was the right answer, which is kind of amazing when you think about it. So we talked about the crust being about 5 kilometers thick in some places and then 70 kilometers thick in other places, and on average it's probably around 20 or so if you averaged it out. But this image here is in miles. This is the only one I could grab that had all these interesting things on it. So we have to kind of mentally convert all of these numbers into kilometers in our head. But over on the far side here, just kind of above my head, is the Kola well in sort of northern Russia. And they wanted to see how deep they could dig. So they started digging, and they got down to 7.6 miles, which is about 12 kilometers. And at that distance, the temperature was so hot that it started to have really negative effect on the drill bits, essentially kind of melting the drill bits. It was so hot down there, which is pretty interesting. So there's some other ones in the USA. There's another well that's about 6 miles deep, so close to 10 kilometers. The ocean crust is a lot thinner, which is interesting, and the furthest we've ever been through there is about 5,000 feet, which isn't a mile even. And then the deepest natural thing that we've ever found is a cave in France. It's about 5,000 feet deep. So there you go. Yeah, it's kind of something we take for granted. We live in this tiny little envelope on the surface of Earth. If you go up 12 kilometers, you're in space. If you go down 12 kilometers, it's so hot that you'd literally just ignite and burn. So, we don't really have a lot of area on the surface of our planet to live in. Pretty crazy when you really think about it. And we haven't really explored that much in terms of below our feet. We know a lot about, what's on the surface, but we don't know very much about what's below the surface. And there's some reasons for that. we can't just go down there. There's no easy way to get there. So anytime we want to go down there to do something, we have to drill a hole, and that is a lot of work. So we're going to talk a bit about the tectonic plates today, which is some pretty interesting stuff as comes as a result of them. So remember we talked about the crust being anywhere from 5 to 70 kilometers thick. The crust under the oceans is very thin. And that really makes sense. If the crust under the ocean was really thick, well, there wouldn't be an ocean there. You'd have a continent. So where we have continents, the crust is very thick. And where we have oceans, the crust is very thin. If the crust were any thicker, then you'd have a continent. So that kind of makes sense when you think about it. There's two more words, lithosphere and asthenosphere, which are written over on the side here. And this is where the layers of the Earth gets really confusing. So far we had the crust, we had the upper mantle, lower mantle, outer core, inner core. That all made sense. You're like, got the crust, perfect. Outer mantle, inner mantle, or upper and lower, I should say, and then outer core, inner core. That's good, perfect. Then we get these ideas of lithosphere and the asthenosphere. And there's something that happens at the upper mantle. The upper mantle isn't the same consistency from all the way from the bottom to the top. The upper mantle is actually broken into kind of two parts. So the lithosphere is the crust, so any continental crust or oceanic crust. And then the very top part of the upper mantle here is solid. It's kind of like what we consider the crust to be, so kind of like rock-like. So you can see this top portion of the upper mantle, about 70 kilometers or so, the upper mantle is this kind of hard stuff. And then you get this, it's called the MOHO discontinuity. So a distinct line exists in the middle of the upper mantle or somewhere near the top of the upper mantle where you get this break, and it goes from being a solid, kind of like a rock in this lithosphere part here, and then you get kind of a molten layer down here. So the lithosphere is kind of like a boat, and then the asthenosphere is kind of like the water that it floats on, but it's not really water. So when we talk about the layers of the Earth, it gets really confusing, and I rightly get confused because you have these layers, and then you have this upper mantle, and the upper mantle is actually broken into two parts, the lithosphere and the asthenosphere. So the lithosphere is kind of like the boat that everything kind of floating on the asthenosphere, which is down a bit lower. I'm so glad you asked that question, Alex. How do we know what this looks like if we can't go down there? So remember we've gone down 12 kilometers, so we're right here. This is how far we've gone. Barely even scratched the surface. We've never been there, but we can take indirect measurements. And this is how we find out so much about science. We propose a theory, we test it, and then if it, becomes true, or if the results support what our hypothesis, then we call it a theory. Now, we have no way of knowing for sure, but we have developed the scientific method. We propose a hypothesis, we test it. If it becomes true, it becomes a theory, until we can prove it with certainty, and then it becomes kind of like a law of nature, if you will. So we do lots of indirect measurements. We'll look at how we can use earthquakes to help us figure out what's down there. We can set off explosions, and basically the waves will travel down and then they'll bounce back up, and we can see what happens as a result of those. There's lots of really indirect ways we can use to measure, but the truth of it is we just don't know for sure. And that's why in science we have lots of different theories about how things work, which are supported by evidence. And until we can verify for sure, it just stays as a theory. So this is science, right? Science in general. Okay, so the asthenosphere is this molten layer that everything kind of floats on. It's like magma as you think of it. And then basically there's all this heat in the upper mantle, and that heat is a result of radioactive elements. So we're going to talk a bit about radiation after the chemistry unit, but this radiation, it creates heat. If you think about nuclear power, that is heat that we're using. We're trapping that heat and creating energy out of it. Same idea here. We're using this heat caused by all these radioactive elements that exist down there, keeps everything liquidy. So, Abby, you're talking about the new gravitational waves that we just discovered a couple weeks ago, which is exactly what I'm talking about. Einstein, almost 100 years ago now, he proposed this idea of gravitational waves. He said these waves exist. Here's the math to prove it, and it became a theory. And people are like, well, yeah, it's a good way of describing how things work, and wouldn't it be cool if we could actually verify they exist? And it wasn't for almost 100 years later. We now have the technology where we can do these really intricate, highly detailed experiments where we have these essentially evacuated tubes under the ground that are kilometers long, that have interferometers in them, which are basically laser beams bouncing off mirrors, and the gravitational waves kind of disrupt those laser beams a little bit, and they cause an interference type pattern, and we can prove that these gravitational waves exist. We've only ever seen it happen once. There's a couple black holes that were kind of orbiting each other, creating these gravitational waves that were so strong that they made it to us. And yeah, so that's exactly what we're talking about. We now have the technology to prove it. And maybe we don't have the technology right now to drill down into the earth to figure out what's there, but we have theories, and we'll support those theories with what we can until we have the technology to create evidence to make them no longer theories. So, we talked a little bit about this when we were dealing with the Mid-Atlantic Ridge. So we looked at those pictures of Iceland where the actual continents were being pushed apart. And this is actually what's happening kind of under the ground. So we'll take a little look under the ground. You have these tectonic plates. So you have this lithosphere kind of floating on the asthenosphere, and they're kind of floating around, and you get these big plumes of magma pushing up, and they rise up and they start to kind of crack the surface. They crack the plates a little bit, and the plates start to get pushed apart. So you can see this happening here in kind of steps. You get this big rising plume of magma, convection current, and it starts breaking through. So these are like volcanoes. Remember, this is on a really large scale. And as they get pushed farther and farther apart, you end up sometimes with a valley here, or all the time. And then as that valley forms, water will fill it in. So it becomes like a lake or an ocean. And then as they get pushed further and further apart, you get ocean. And these plates are constantly moving apart, and new magma is filling in the void here. And it's creating oceanic crust in the middle of the continent. So this is exactly what happened between North America and Africa, and South America and Africa. You had this big rising plume of magma pushing these plates apart, and it's called ridge push. The plates are constantly slowly getting pushed apart by the magma in the middle, and there's constant new oceanic crust being formed between them. So that's exactly why you end up with underwater volcanoes. There's some other reasons, but this is the main cause of that. So we call it ridge push. You get a ridge in the middle because all this magma is pushing it up. So even though they're separating, they're getting spread apart, because there's so much magma pushing up, they kind of have a little kind of ridge in the middle. And the water gets there from rain, or the valley could open up so far that an ocean can start to fill it in because it's lower than sea level. Remember, the continental crust is really thick. And if we start replacing that really thick crust with really thin oceanic crust, it's not oceanic crust right away, but this really thin crust, all of a sudden it's lower than this thick crust, and water starts to fill it in. Remember, these things are happening over millions of years. So yes, it is a lot of rain, but even if it rains, a meter a year over 1 million years, that's 1 million meters of water. What happens to it? Well, it rains, it follows kind of the lowest path to an ocean. If the Rift Valley is the lowest part, it'll fill up. If it's really hot, it'll evaporate. It just depends on where it is. So these processes take place over millions of years. We talked about the continents moving apart about 1 centimeter or 2 centimeters a year. We're talking extremely slow processes here. So very long periods of time these things are happening. So that's ridge push. There's two methods of things that cause these plates to move. So ridge push is the first one, and then the second one is slab pull. And you end up with a push, you got to have a pull. It's just how it goes. So if you think about tectonic plates, you get this big push in the middle and they start to spread apart. Well, it's moving away from the center. What happens at the other edge? You have these big plates, so this plate's kind of moving away from the center. What happens to it? Well, it's going to bump into something over here. That's what this image is showing. The image is showing your ridge in the middle, so you have this rising plume of magma coming up, and you get this plate, oceanic plates getting formed, but this is moving constantly. Now you get this really thin oceanic crust, and it bumps into a really thick continental crust. What happens? Well, if you take something really big and you push something up to it that's really small, think about cars. If you take like a big, huge truck and you take a little smart car and they have a head-on collision, what happens? Well, the big truck just runs right over the smart car. The smart car goes underneath. And that's what's happening to the continents. So as they are getting pushed apart, the other edge on either side, it bumps into this really thick continental crust and it actually goes underneath it. And if you've ever set the table at your house and you put on a nice tablecloth, but you have like a really smooth table. I know this used to happen to me when I was a kid. And that table is really smooth. And then your tablecloth's not exactly centered. It's kind of over onto one of the sides. And then it starts to kind of fall off the edge. You know, gravity pulls it off. And then all of a sudden it just keeps tumbling and just goes whoosh right off. That's kind of what's happening with these plates. So you get the push in the middle, the ridge push, the plate gets pushed along, and then when it hits the continental crust, it dives down underneath. And once it starts to go under, it just keeps going under, and it just keeps pulling the rest of the plate under. So you have kind of two things happening. You get a big push in the middle and a pull on the other edge. So these are the things that are happening when plates kind of interact. So this is what causes the plates to move. You get these big plumes, cause the push. Once it starts to go under, you get a pull. And what you get here is a subduction zone, it's called, where one plate subducts under the other one. This is called a subduction zone. And some interesting things happen at subduction zones. So this is where you end up with lots of earthquakes and volcanoes being produced. Once this slab starts to go underneath, it gets hotter and hotter, and all the friction here between this oceanic plate and this continental plate, the temperature is just immense, and it melts and basically turns back into magma, and then it rises again, and this oceanic sort of situation here just keeps kind of getting recycled. It rises up, becomes solid, where it's nice and cool at the surface, you get a lot of friction, heats up, melts again, and then rises back up, solid, melts again, and it just keeps getting recycled. So that's what happens with these plates. So let's slab pull. So these are the two methods which you'll end up causing these plates to move. Ridge push, slab pull. Those are the two ways they move. The continental plates kind of just float around. They're just kind of hanging out. So this is an image of the main plate boundaries, and I like this image because it's nice color coordinated. The image from your data booklet looks a little bit different. So if you have a data booklet somewhere near you, you might want to grab it. If not, I'll just come back to the image and we can go from there. What goes into the place where the plate used to be? So that's kind of right here. You're talking in the middle of this Rift Valley. You get new magma rising up, and then it comes to the surface where it's nice and cool and it solidifies. So the plate used to be here. As this plate moves, new magma is constantly being deposited on this edge, forming new rock. So this rock's really young, and then as it gets over here, it gets older, and then it gets born again, really young, older, and you get sediments and things like that being deposited over long periods of time. So this gets back to the idea of magnetic striping that we talked about last day. As that new rock gets deposited, the magnetic north pole is pointing this way, and then it gets pushed apart, and then the poles will switch about every 100,000 years, and now the pole will be pointing the other way, and then that gets pushed apart, and then a new pole, and then pushed apart, and you just get this striping. Is it in water when it happens? Generally speaking, these rift valleys, the ridge push will happen underwater, but not always. We'll look at an example here in a second where it doesn't happen underwater. And you guys will be experts on looking at this stuff. So this is kind of the major plates. There are lots of minor plates that we don't really talk about. We're just concerned with the major ones. So you can see all of North America's major plate, South America, Africa. Off our coast here, we have this little plate. It's called the Juan de Fuca plate. And if you've ever been down to like Victoria area, it's the Juan de Fuca Strait is between Vancouver Island and the mainland. Gets its name from the plate here. There you go. Yeah, so the only one that's there's a couple of smaller ones here like Saudi Arabia and India have their own little plates. But generally speaking, the plates are pretty big. And this image here, this next one is from your data booklet. So this is kind of the one that you get on tests. And you should be able to identify what's going on. Now, at the very end of my presentation here, I say the symbols are important, but we should talk about them now. So we haven't talked about the names of these things yet: divergent boundary, convergent boundary, transform. We're going to do that in a second. But you have this, a set of labels down here, a key at the bottom of your map. And you should know what these things are. So a divergent boundary is these two lines. So in the middle of the Atlantic, you have a divergent boundary. And then a convergent boundary, these little triangles on the lines, kind of off the coast of South America here. Transform boundary is just a straight line. You end up with one kind of over here. There's some other ones right here. And then mountains and volcanoes are pretty straightforward. And there's giant arrows that show you where the plates are going, in what direction they're generally moving. And here is just another page from your data booklet, but it's just our neck of the woods sort of idea. So specific to British Columbia off our coast. So you can see that you have all these volcanoes in BC, but you think, I didn't ever think that BC was a seismically sort of significant place. But yeah, there's tons of volcanoes in BC. A lot of them are dormant, but there are a lot. If we go down towards Washington State, the Cascade Range is kind of the extension of our coast mountains up here. You've been to Vancouver, you've probably seen Mount Baker in the distance, which is really close to the border. And then we're going to talk a little bit about Mount St. Helens next day, our kind of active volcanoes that are, I say Mount St. Helens is more active than Baker. Baker's fairly dormant these days. But there you go. So that's our neck of the woods. There are some volcanoes really close to Vancouver, actually, which is a big deal because there's millions of people that live in the Lower Mainland, and they're very close to a dormant volcano. So we'll talk a bit about that. So the plate interactions, there's only so many things that can happen when you have two plates come in contact with one another. So they can move apart, which is divergent. They can come together, which is convergent. And they can slip past each other, which is transform. So these are the three different types of interactions you can have. It seems like, there's only three, that's easy. Well, we run into but you can have different plates bumping into each other. So you can have continental plate, like a real thick one, and an oceanic plate. What happens when they bump into each other and move apart, or you end up with different types of plates interacting. Ava, wasn't there a volcano in West Bank? Yeah, there's an ancient, really, really old fault line that runs down pretty much the middle of the Okanagan Valley, so under the lake. And there's a few volcanoes that are there that existed before the last ice age. So if you've ever seen Mount Bushery, which most of you have, it's kind of a really sort of reddish dark color. That's because it's a caldera. So in the middle of a volcano, you have this big magma chamber. And that magma chamber filled up with magma, and then it cooled and became this really hard rock. And as the glaciers came through the Okanagan Valley, it scraped the top of the volcano off, and that really hard rock that was left in the caldera was left over. So Mount Bushiri is the caldera of an ancient volcano. If you look the other direction, if you look towards sort of Big White up Highway 33, Black Mountain is black. Why? Well, it's a caldera of another volcano that used to exist here as well. So a long, long time ago, our area used to be volcanically active, but we're talking long time ago. All right, let's look at the different types of plate boundaries. Divergent boundaries are where you get plates spreading apart. So on your map or on the data booklet, there'll be two lines, kind of parallel lines, and that'll show a divergent boundary. So you end up with oceanic ridges, so we call it the Mid-Atlantic Ridge. That is a rift valley that's under an ocean. If it happens on land, it's called a rift valley. So we end up with sort of two names for the same thing, depending on whether it's on land. If it's on land, it's called a rift valley. And then if it's under the ocean, it's called a ridge, an oceanic ridge, because you get this little, like a valley under the water, but because it's being pushed up with all this magma, this plume underneath, you end up with a tiny little ridge. So if you have your data booklet nearby, I can go back a couple slides to the picture. In chat, just find a place where you've located a divergent boundary. So look for the symbol. Let's use this map here for now. So the symbol for a divergent boundary is here. Where are all of the divergent boundaries on this map? Can you find a divergent boundary? Obviously, there's one down the middle of the Atlantic. We talk about that one a lot. But can you find one on land? Is there any divergent boundaries on land? Where is it? Find it. There is at least one I can think of. That's all I can think of, actually. That's all I can see as well. There's one divergent boundary on land. So you have a rift valley being formed on land. Eurasian plate. Eurasia's here. I'm not seeing one on the Eurasian plate, but right here, unless you're talking about down here, which is actually this Saudi Arabia has its own plate. And then right here in Africa, you have this rift valley, Arabian. There you go. So the Arabian plate is being kind of separated here. So right along this rift valley, you get a bunch of volcanoes in Africa because this plate is kind of being separated right now. So this is kind of the main spot in the world where you end up with a divergent boundary on land. There's actually one other spot, and we actually talked about it last day, the Mid-Atlantic Ridge. It runs right through the middle of Iceland. So if you go up here to the North Atlantic, you end up with this tiny little island of Iceland, has this rift valley in the middle of it, and there's tons of volcanoes on it. It's highly volcanic because you have these plates spreading apart and magma forcing its way up. So there you go. Those are your divergent boundaries. So you're looking for parallel lines. This is it's called the East African Rift Valley. So this is an actual photograph from the air of this rift valley in Africa. So you can see the two plates here, the edges are moving apart, and in the middle you end up with volcanic activity, which is kind of interesting because the volcanoes in rift valleys aren't just one volcano. Kind of, you think about like when somebody says volcano, in your mind you think of these big towering cones like Mount Fuji or Mount Baker, big rising up from the ground, huge pointy volcanoes. Well, that's not what happens at these rift valleys. You have really long distances where the plates are moving apart, and in the middle you get all of these volcanoes popping up all the way along the rift, down its entire length. So above my head here, you can see you have this huge plume underneath Africa, and it's rising up and it's pushing Africa apart. And you're ending up with this rift valley. And I think we were asking earlier, well, how does it fill with water? Well, it isn't really below sea level yet, but as these plates get separated farther and farther apart, and as this new magma gets deposited in, it's going to be very thin, and the ocean's going to eventually fill it up. So down here below, you kind of see it happening. These red lines are showing the rift valleys that are forming as a result. And in a couple million years, you're going to end up with Africa, which is right here, which would normally come up like this. It's going to end up being a big inland sea or an ocean. So as these plates get separated further and further, this red line is going to eventually fill with water, and then you're going to end up with this little piece just kind of splitting right off. So it's going to become a big island. So that's a rift valley on land. That's what it looks like. So kind of interesting. Whew, that's a lot of writing. Convergent boundaries are a little bit more varied. So when you have a divergent boundary, it's going to be underwater or it's going to be on land. And those are the only choices. Yes, Somalia will become an island millions of years from now. Interesting? Possibly? Yes. There's some evidence to suggest that it might not, but for the purposes of this class, yeah, it'll become an island. It's complicated, right? It's difficult to predict what the weather is going to be like in 5 days from now. Trying to predict what the Earth is going to look like in 100 million years from now is kind of like we use computer models to predict it, and we can look at what's happening now, and we can, broadcast that into the future, but there's no guarantees. The Earth is a complex thing. These are very complex cycles, and you end up with some unknowns that we can't fill in. So we do our best to describe it, but we're not perfect. Okay, convergent boundaries. So when plates come together, divergence, easy. You have it on land, you have it under the ocean. That's it. There's the two options you have. When you have convergence, so plates coming together, there's three options. If you have a thick continental crust and a thin oceanic crust, and they come together, this is the giant Hummer running into the tiny smart car. The Hummer just goes boom right over top of the smart car. Smart car goes underneath it, and you get a subduction zone. So right behind me here, you get this subduction happening where this plate gets the slab pull underneath. And right here, all of this rock is under immense temperature and pressure. So it becomes really, really hot. What happens when things become hot? Well, they start to rise. So they rise up to the surface and they break through the surface. And this is where you get volcanoes. So instead of it just being one volcano, like Mount Fuji or Hawaii is a good example, you get really long strings of volcanoes. So this is very common all around the world, where you see an oceanic plate getting pushed under a continental plate, and you get a long line of volcanoes. So we'll talk a little bit about the notes here, and then I'll show you some examples of this on the map, or you guys can find them. So the oceanic plate's denser. The continental plates are kind of fluffy and light. Not really, they're made of solid rock, but oceanic crust is really dense, whereas continental crust is a lot lighter, less dense, I should say. So because it's running into it, you get subduction. It goes underneath, and that subduction zone is where you get things like volcanoes and earthquakes happening as the plate kind of slides underneath. It gets caught, and then it gets going again, and it gets caught, and then it slides again. And it's constantly happening, very slowly. So most of the mountain ranges in British Columbia are formed as a result of this exact process. So British Columbia would normally be just nice and flat, but you get things like the Rocky Mountains. The Rocky Mountains are fairly old mountain range, but they resulted because that Juan de Fuca plate, or the Pacific plate, I should say, was getting pushed underneath our nice thick North American plate. So you end up with this immense pressure and this immense temperature, and this rock starts to become liquid again, and then starts to work its way up through the surface, and you get these really long chains of volcanoes. So volcanic belts or volcanic island arcs, if you can, on your data booklet, if you have one near you, or I can just jump back here, can you find an example of a chain of islands that is as a result of a convergent boundary, an oceanic plate diving under a continental plate? Can you find an example of that in your data booklet? I know there's some examples here in the notes. but can you find it happening anywhere else? There's a couple in our neck of the woods that are fairly common. Some other famous places that are known to be volcanically active. So if I look at just our neck of the woods here, just BC, up in the north, if you guys have ever seen the show where they go fishing for crab, Deadliest Catch on Discovery Channel, this is a good example of it. So the Pacific Plate is diving under this North America plate up here, and you end up with this, Abby and Taylor, you're both right. We'll get to them in a second. You end up with this subduction zone. So these triangles is a convergent boundary, and because these plates are coming together, you end up with this oceanic plate, the Pacific Plate, diving under this continental North America plate. And what you get is the Aleutian Islands, which form this volcanic island arc. So this is called the Aleutian Trench, where you end up with this stuff happening. So that is an example of that happening up in Alaska, Bering Sea up there. If I jump back one further, so these were the examples you guys were talking about. Abby mentioned the Nazca Plate, if I can find that. We were just looking at that. Oh, here it is. Abby and Taylor both saying the same thing. So this is a perfect example of it. You have the Nazca Plate, which is being pushed here by a divergent boundary, so being pushed along, and then it's running into this really thick continental plate. It's running into South America here, and it's diving underneath it. And the mountain range that's formed here, does anyone remember what the mountain range is off the west coast of South America called? When do you learn about mountain ranges? It's got to be like grade 7 or 8. I remember having to memorize those when I was a kid. So you get these volcanic arc being created as a result. These are the Andes Mountains of South America, Chile. So that's happening there. Another example kind of happens over above me here. The Pacific Plate's also running into the Eurasian Plate, and this is why Japan is so seismically active, because you end up with this plate getting subducted under it, and you get all these volcanoes that form that created Japan. And then even down here, you have Indonesia having the same sort of thing, and the Philippines. The Indonesian islands are these, the chain is formed because of subduction happening. So there you go. Those are kind of the big, thick continental plate, the tiny oceanic plate, and they get subducted underneath. So we did that. Oceanic plate convergence. So if you have two really thin, really dense, but really thin oceanic plates, they bump into each other, what happens? Well, one wins. One will eventually go over top of the other one, and one will get subducted underneath it. So you end up with oceanic subduction happening as well. And this is where you'll get these really long chains of volcanoes, like the Aleutian Islands that we were talking about, Japan, Philippines, Indonesia, all exist because of oceanic plate convergence. So you get a volcanic island arc, and they just turn into long chains of volcanoes at the subduction zone, this big trench that gets built up here. So colder, denser plate will get subducted under it, and then you end up with long chains of volcanoes. So eventually the volcanoes will break through the surface over millions of years, and you end up with long chains of islands. So the Aleutian Islands, Japan, those are great examples of this oceanic convergence. So thick continent, thin oceanic goes under. Two oceanic plates, the denser one will subduct and you get islands formed. And then we're going to look at the last example of convergence here in a second. Notice, though, that the islands don't form right at the trench. These volcanoes or the islands actually form a little ways away because as this plate gets subducted under, this heat and magma starts to rise up, but it doesn't rise up right at the point where the plates meet. It takes a while for it to melt and rise up and ends up right here. Abby, Hawaii is actually an example of a hotspot. And we'll talk about hotspots in the second half, possibly tomorrow, not sure. See how far we get. And hotspots are really cool. I'm going to look at a couple of those, but not an example of subduction. And if I jump back to the map here, you can see Hawaii is actually in the middle of a plate. So the